Hello, everybody, and welcome to this event. My name is Juliane von Scherpenberg. I'm a PhD student at the Max Planck Institute for Physics in Munich, and I'm a member of the MAGIC collaboration. So what is the MAGIC collaboration? We are an international collaboration, and we operate two beautiful telescopes on the island of La Palma in the Canary Islands. And with these telescopes, we observe the high energy, most extreme universe. We are a big collaboration with members from all around the world. So you can see we have members from all over Europe, but also in Brazil and India and Japan. And usually twice per year, we try to meet and give feedback about the science that we've been doing and share our latest results with our collaboration members. And during these meetings that we have, usually we try to organize one event where we share the science that we do with the public. And we do this in a relaxed environment, like a bar or something similar. Well, this year, everything is different. So this year, of course, we are having our meeting online in a virtual format. And of course, we also have to do our amazing outreach event in a virtual format. So you will have to take care of the relaxed environment. I hope that you have a nice beverage, no matter where you're joining, either a beer or a coffee next to your computer, and have a relaxed time, and you will enjoy this really nice event. Actually, we have chosen an extremely interesting and hot topic for this event, namely the supermassive black hole at the center of our galaxy. As you might know, the Physics Nobel Prize this year was given to Roger Penrose for the discovery of the black hole formation, that the black hole formation is a robust prediction of general relativity, and to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. And we are very thrilled to have as our first speaker today, Felix Wiedmann. Hello, Felix.
Hello.
He is a PhD student in the group of Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Garching. And as a member of the gravity collaboration, he works on improving the gravity instrument, and he also studies the effects of general relativity. And yes, as a second speaker today, we have our very own Christian Fruck. Hello, Christian.
Hello.
He is a member of the MAGIC collaboration since 2011 already. And currently he is working as a postdoc at the Technical University in Munich, where he's also working with the IceCube collaboration and on the new next generation neutrino detector called P1. Yes, thank you to you two for being here, and I think we will have a great time. We will shortly now start with our presentations, and just remember, everybody, you are very free to ask any questions you might have in the comments or in the chat on YouTube. We have two beautiful people working here backstage. They will keep track of all of the comments, and we will have time at the end after the two presentations to answer all of your questions. So without further ado, let's start with Felix's presentation, and he will tell us all about the observations that led to the Nobel Prize and what we have learned since then. Felix, the stage is yours.
Thank you. I hope you can see my screen. I started sharing the presentation. Thank you again for having me here. I'm very happy to tell you today a little bit about the supermassive black hole in the galactic center. As you already said, Julie, I'm part of the gravity collaboration. I'm a PhD student here in Garching, close to Munich. And I'm very happy to give this talk today on behalf of the collaboration. So let's start with a little bit of context and a little bit of history too. So what you see on the screen is an artist's impression of our Milky Way, which probably looks kind of like this. We're not entirely sure. Where we are is here in this little spot to the bottom. There is a little label called Sun. And so we are about 30,000 light years away from the center of our galaxy. And a question which has been there since quite a while now is what is actually in the center of our galaxy? Today, we know, or we think to know, that at almost all massive galaxies have a supermassive black hole at their center. But this is actually not that long since we are convinced that this is the case. In the case of the Milky Way, very early people started to wonder what is in the center, and the first detections were made actually in radio already in the 30s, in the 1930s. The picture you see here on the right has a bright spot in the bottom right where the center of our galaxy is, which we call Sagittarius A star. This is, of course, not from the 30s, but a comparably recent picture. But yeah, I said already in the 30s, we knew that there is a radio source in there. And over the years, people observed it. And I think in 1974, it was for the first time made the claim that our galaxy hosts a supermassive black hole. So the question is, what is here in the center? Is it really a supermassive black hole? And it's not so easy, obviously, to observe a black hole, to prove that there is a black hole, because as the name said, it's an object which is black. It's an object which is extremely dense, which has an unbelievable amount of mass on a very, very small area. That's basically how we define a black hole. And now I want to take you on a bit of a journey to explain you how we know that, or how we think to know that there's a black hole in the center of our galaxy. What you see on my screen currently is a picture of the Milky Way. This was taken in Chile at the Paranal Observatory, where we make almost all of our observations. And the dark and bright band you see ranging over the sky is the Milky Way. And very conveniently, the laser of one of the telescopes is actually pointing exactly to the center of the galaxy. So where this little yellow laser pointer is going to, that's where the center of our galaxy is. This is, you probably, if you're looking at the sky in Europe at a very dark night, you might see a little bit of the Milky Way. But to really go and observe the center, you have to watch much, much further in. And that's what you see in this video. You see a zoom in going into the galaxy. We're moving further and further in, and you see that there are an insane amount of stars. We're moving towards the center very, very slowly. This is a journey of 30,000 light years, and in the very center, there's this very bright spot with all the stars. And what we actually observe are the stars in the very, very center of our galaxy. Julia, I have actually no idea if you're still playing the video or not, because I don't see it. But I just gonna assume no and continue with what I want to show you. So what you see here on the right, hopefully, is kind of the very center of our galaxy. And this is a real observation done with an 8-meter telescope in Chile. And then to the left of it, you see yet another zoom into this very little red box in the center. And the GIF you see moving on the left side is a combination of observations over 20 years. And you see that the stars at this point are not stable, but they move around. And I want you to, oh yeah, exactly. And this is basically what the team of Reinhard Genzel here at MPE has done for the last 30 years, is to observe these stars and map the movements of the stars, learn about them, and try to understand what there is to learn from them. And at the same time, also over almost 30 years by now, another team led by Andrea Ghez at the UCLA in California has done more or less the same. They use the telescopes which are based in Hawaii, and we use the European telescopes in Chile, in the north of Chile. And why this effort? I already pointed out that those stars are moving to the left, and I want you to focus on the star which is highlighted here with the red ellipse. It's the star which we call S2, or sometimes referred to S2 as S02. And you can clearly see that this star is on a bound orbit. It's moving around in a circle, and you can imagine it very similar to how the Earth moves around the sun. Also, in the same fashion, this star is moving around an object. If there wouldn't be an object in the center, the star would just fly on a straight line. But from the orbit of the star, we know that it has to be bound, that there has to be an object in the center. And Julia would ask you to show the other video where you can see another zoom into the stars. And this video shows you that we not only know this one star, but we actually know the movement of a lot of those stars. So every star you see in this simulation, which is done by the Department of ESO, every star which we see in this simulation is actually observed by us. And as we move closer to the center, you see this green lines popping up where the orbits of stars are known. And you see that we don't only know one orbit, but we know, I think, up to 45 orbits of stars right now. And all these stars, they move around the very same object in the center of our galaxy. And this, so from mapping these stars, from observing their movement over almost 30 years now, we know that there is an object in the center of our galaxy, which is very, very dense, which is mostly dark. I'm saying mostly, that's something I will come back later. And from observing how the stars move, we can actually also say how heavy it is. By measuring the movement of the stars, we can run our fitting machines, we can calculate how heavy the mass in the center has to be. And we know that this mass in the center has to be 4 million solar masses heavy. So what we know, we have an object which is very compact. We basically can't see it, and it's 4 million solar masses heavy. And there is basically only one reasonable explanation to this, which is that this object in the center is indeed a supermassive black hole. And as we already heard in the introduction, this was also what the two leaders of the team, Andrea Ghez and Reinhard Genzel, rewarded half of the Nobel Prize this year for the discovery of a supermassive object at the center of our galaxy. And I kind of want to point this out because nowadays we are very common to the idea that we know that supermassive black holes exist. But this is really one of the very key observations. Without these observations, we wouldn't be that sure that supermassive black holes in general really exist. They were predicted by general relativity. The math was done almost 100 years ago. So it's very clear that they should exist, but that they really exist is really shown by this observation. And that's also the reason why the Nobel Prize was awarded for this year. But now we know that there's a supermassive black hole in the center of our galaxy. And you might wonder, what is this helping us? What do we do with this information? And from a physics point of view, this is really helping us a lot because we know that there is a mass of 4 million solar masses. That's something you can't even imagine, yet you don't have available at Earth. And we know that there are stars flying in orbits around. So we can use these stars basically as test particles to test how gravity works in such a regime, how general relativity really works, if the theories done by Einstein are really right, or if we can maybe say close to a supermassive black hole, this is not holding up. We see some deviations, we see something different. And in order to do this, we want, of course, the best possible telescopes. And the observations I've shown you so far were done with mostly 8-meter telescopes. What you can see here is an array of 4 8-meter telescopes. So we used to use only one of those. All those telescopes, the picture you see right now is from Cerro Paranal in Chile. And what the team here around Reinhard Genzel has done over the last years is that they built a new instrument, and that is called gravity. You see a picture here of gravity on the right. It's a cryostat. It's not looking super impressive. but it's actually not at one of the telescopes, but it's placed in the middle of the observatory in the lab below the ground. And the reason why it's there is that it combines the light of all 4 telescopes. So we don't only use one telescope anymore, but we use all 4. And we're doing optical interferometry with gravity. And that is basically a way of observing, which is very normal in the radio, but very tricky to do it in the optical. It basically simulates of 4 telescopes that you have one big telescope. And the cool thing about this is that in interferometry, your sensibility is as good as the distance between the 2 telescopes. So we basically can simulate a telescope which has a diameter of 130 meters. So we are with gravity much more sensible than what we would, or we can reach much higher accuracy actually than what we could actually do with one 8-meter telescope. And when I tell you now that gravity has the resolution of a 130-meter telescope, that's probably really hard to imagine. So our usual example to put this into context is if you look at the moon and if you put a football stadium on the moon, then it kind of has the same size on sky as the S2 orbit for us has. So the orbit of this star moving very close around such a star. So you see already that's pretty small. But if we now look how well we can measure stuff with gravity, this is actually down to 10 microarcseconds. And that is the same as if you would point a euro coin on the moon. So if we would observe, has to be very luminous, but if we would observe an object on the moon, we could tell to about 1 or 2 centimeters where it's exactly placed. And that's really one of the key things is this great increase in accuracy with gravity for the results we can achieve now. And to illustrate that a little bit, this is the animation you have seen before where we see S2 flying around such a star. This is done with one 8-meter telescope. And now if we zoom into this very little box here, we can actually see the gravity data to the right. And this is now data taken over 1.5 years. To the top right is when the star, which is moving around here, is to the top right. That's in April 2017. And then when it's to the left, that's in July 18. So we actually see over 1.5 years how the star S2 moves around the central object, which is such a star, which is the second source here in the middle. That is actually the supermassive black hole. And you're hopefully a bit surprised that there is light coming from the place where I tell you that such a star is placed. And I will come back to that in a little bit. But first, let's look at the real data. So this is the ellipse you can see on the left is the orbit of S2. And all the black and blue points are the data points which we have taken. And the little cross here down to the center is where we think that such a star is, where the center, the mass center of the supermassive black hole is. And if we actually zoom in a bit to this very region around the supermassive black hole, you can see here the gravity data points in blue. And what's actually really amazing about this data is you see here I marked the dates when it was taken. And for example, here from June 1st to June 3rd, you see a really big movement of S2. So when we were observing at that time, we really saw from one day to another, or within 2 days, we saw a significant movement of the star, which is something really, really rare in astronomy and is just possible due to this amazing sensitivity of gravity. And now I told you that we use gravity, we use this star S2 to test general relativity. And one of the things we wanted to test is shown in this simulation here by ESO. We see the black hole in the very center as this dense black region and the star S2 flying by. And one thing which is actually predicted by general relativity is that when the star crosses through the gravitational field, that the light of the star changes color. The star basically gets redder. And you can imagine in a very simple way that the light has to get some extra energy to leave, it needs some extra energy to leave the gravitational field, and that's why it's getting redder. It's an effect which is very clear here, but it's, of course, in real life, a very, very small effect. And how our data looks like is that we always compare what would the data of the star look like if it would be totally Keplerian? So if there is no redshift, if there is no general relativity, that would be the blue line at the bottom. And if we have a redshift, then we would see the data following the red line. And if we now fill in our data, we see that very, very clearly that the gravitational redshift is observed. And that was we published this in 2018, I think, 2 years ago now. That was the very first detection of gravitational redshift close to a supermassive black hole. So this was kind of the first, or one of the first GR effects which we observed in the galactic center. But then you can, of course, move on and say, okay, what's the next effect, the next general relativity effect, what one can see? And this is shown here. Maybe if you know a little bit about general relativity, you know that already in Mercury, we observed that the planet is not on a constant ellipse around the sun, but it actually precesses a little bit. So every time when an object comes close to a heavy mass, every time it crosses the mass, it kind of ticks a little bit over. And that's what you can see here. Our star S2 is not on this red orbit, which would be without GR, but actually every time it crosses down the black hole, it ticks a little over. And over many, many years, it shows this Rosetta shape on sky. This is, of course, again, an artist animation. How it looks in real life is if you look very closely on this ellipse I've shown you before, you see here in the very top left that the two lines actually don't really close. So the ellipse is not closed. And this is actually what the Schwarzschild precession looks like for us. So this was the second effect of general relativity, which we wanted to observe and which we observed, or which we, with the data, we published that last year. And you can then again make the same graph as I've shown you for the redshift. You see here the blue line would be without a Schwarzschild precession, and the red line is when we think that general relativity is really true. And we see very clearly that the data follows the path shown by general relativity. So this is just an example of our two main results, which we have done over the last year, to illustrate to you that the supermassive black hole is really a great way for us to test general relativity. And we're, of course, just getting started with this. There are more effects which we want to test. Our measurements have to get more precise in order to get to the next order of these effects. And then one thing I shortly mentioned earlier is that we might actually be able to see Sagittarius A star. So I've shown you this little animation of our data where the star S2 is flying by. And in the very center, I told you that this is where Sagittarius A star is. And as you can see, it's not a black point on the sky, but we actually can see some emission. And you see it's flickering. It's not staying at the same luminosity as the stars. And I have another visualization of our data, and this was taken in June last year. I was actually at the telescope observing at that point. And you see here in flickering, the brightest source in this image is S2, the star. The flickering is just due to the atmosphere. But the really interesting part is in this white circle below S2. That's where we think that Sagittarius A star is. And if you look closely, you see in this GIF that at some point Sagittarius A star is popping up. You see that there is a source where it's faint, and now it's getting bright. And this is a loop of, I think, something like 2 or 3 hours observing. So what we've learned over the last decades of observing Sagittarius A star is that it has this flux excursions where it gets very, very bright for half an hour or maybe sometimes an hour, and then it gets dim again. And one of the main goals of gravity was to learn more about these flares, which we call them. And the idea was, if we maybe can measure the position of those flares, that we can learn more about where they are coming from and why we actually see them. And this is an observation which we did in 2018. The color shows you the time evolution of the data. And we are now in scales very, very close to the black hole. So the black hole is here at the center, and we're just a couple micro-arc seconds. That's a very, very scale around the black hole. And you see the data, which goes from blue to green to yellow, doing a kind of circle around the black hole. And that's what we believe to see here is really a hot spot, a spot of hot material moving around the black hole, getting brighter by forces from the black hole, and then dimming out after, you see here the data is taking about over about maybe an hour or so. So this is another really exciting result, that we can actually resolve these flares from such a star. We can see them moving in orbit. And on my last slide, I want to show you a little animation again, where we are in this very close environment of such a star. We see here in the middle, where it's basically dark, is where we think that our black hole is. And then we have a very dynamic environment around it. And what we can actually observe is this red blob, which is moving around such a star. And this is this circular motion, which you can see in the flares. And this is basically some kind of probably accretion disk or something around such a star, which gets heated up and then has this very bright flux excursions, which we, with gravity for the first time, can resolve. And that's something where we need more observations, where we need better understanding of what's actually happening. So this is really a subject where we are just starting the understanding now and the observations now. And with that, I want to end my presentation here. Again, thank you for having me, and thanks for listening.
Thank you so much, Felix, for this really nice presentation. I think it is so impressive to see how technology has evolved, how we can resolve these really tiny star orbits around the black hole, and also so nice to always see again and again that Einstein was right. I love seeing that in experiments. We had two very short questions, I think, that we can maybe answer right now. So Hayato Kuroda was wondering if these observations were taken in the optical, so with visible light.
No, all these observations are taken in the near infrared, so at slightly longer wavelengths at 2.5 micrometers. And yeah, I said optical interferometry, but we are doing near infrared interferometry. And the reason for that is that the Milky Way, if you remember this picture I showed, has a very black band in the middle, and this is mostly dust, which is not see-through in the optical. So if you point with an optical telescope, you don't see anything, but it is very see-through in the near infrared. So that's why we observe in the near infrared, to be able to observe the galactic center. So yes, it's all near infrared.
Okay. Thank you, Felix. Okay, so yes, thanks again. And I think we will move straight to our next presentation by Christian, who will talk about, yes, hi Christian. So you will tell us a bit, maybe more, well, first of all, what MAGIC sees when we look at the galactic center, and well, what it can tell us about the past of the supermassive black hole.
Yes, I have prepared for you also a couple of slides, and also we show a few videos. The slides should be visible now. Yes, about my presentation, first maybe about myself. I'm now working as a postdoc at Technical University of Munich in neutrino astronomy and instrumentation. But I'm still, through the Max Planck Institute in Munich, a member of the MAGIC collaboration, where I've done a diploma thesis and a PhD thesis. And basically, since nearly the very beginning, this topic of the galactic center, has followed my scientific career very closely. And the view we have with MAGIC on this galactic center is a bit different than from infrared, for example. So, for example, what you will see is that we cannot, of course, resolve in a similar fashion small structures there in the galactic center. And also the perspective we have on the galactic center is not the same in a sense that what you've seen from Felix is actually a view of the very recent past. This has to be taken with caution, of course, because you know that the speed of light is limited, and what you see there happening, this star orbiting around the galactic center, is actually something that happened tens of thousands of years ago because of that. But it still is something that back at this time happened actually relatively quickly, on the order of years. These flares from the galactic center, this is a time scale of minutes. Or hours, and you can also look you can look further back into the past if you use some other techniques. the thing is that whenever something happens of that violent nature, that's also why the title of this talk, if matter gets accelerated close to black holes, usually it's not only optical light or infrared in this case that's emitted, but it's also electromagnetic radiation across the entire electromagnetic spectrum, especially also at very high energies, gamma rays, X-rays, also charged particles are accelerated. So charged particles, what we mean there are electrons and protons. But this is all not very well known, and this is why we're so interested in studying those objects. So now let me dive into the presentation. This is our galaxy, pictured in a visual spectrum. There are many reasons why I show this. This is, first of all, to give you again an overview. You've seen this already, but it's also to familiarize you with the projection that I will be using in the next couple of slides. Imagine this as a view of the entire sky. So 360 degrees around you, above you, below you, and turn in a way that the galactic plane, which you see across the image here, is actually forming the equator. Imagine this like a world map. You've for sure seen world maps where the world is unfolded and you see the entire globe around the equator folded out like this, that the North Pole would be here, which is, we call this also the galactic North Pole. South Pole is here, and then around the equator, basically the two ends meet again here at the edges. So this is a view of the entire sky. This is in optical. Those are the dark clouds that Felix mentioned, why you cannot see through with optical telescopes. And you see that most of the light we see in the night sky is actually from stars of our own galaxy, but there are also other extragalactic objects. So those are the Magellanic Clouds. And here should be the Andromeda Galaxy, but it's not very well visible in this picture. And then I said that there's not only optical light. So this is now really visual optical light, like you would see it if your eyes would be maybe a bit better than they actually are. But you can also observe in other wavelengths. And for this, I will start with a different instrument, not MAGIC actually, but the Fermi Space Telescope. This is a satellite that has been launched into orbit in 2008. Here is a photograph of the instrument. You see a human for scale. I choose an astronaut because the satellite actually is in space now. If you look into this instrument, this is the Fermi Large Area Telescope. What we are most interested in now is at the top of the satellite here. If you would cut this open, you would see that it actually consists of particle detectors like we physicists are used to from particle experiments on Earth, like, for example, the detectors at the Large Hadron Collider at CERN. More precisely, those are particle trackers. Those are for measuring the direction of the photon mainly. And then further down here, you also have so-called calorimeters. Those measure the energy of the photon. Or more precisely here, actually you detect the photon by detecting all the secondary particles or decay products of those that form when the photon comes from outer space and hits your instrument. The area of this whole thing is just about a square meter, and typically you detect particles that come from the top, first fly through the trackers to establish the direction information, and then you also resolve the energy. The advantage of this is that you can measure energies across a very wide range in energy as compared to optical instruments. But the angular resolution is actually not that good, by far not as good as, for example, of gravity. Yes, but what you see then, and this is what you see on this slide, is again exactly the same view of our galaxy, but it looks a bit different. What's maybe first pops out is, okay, at very first you see that there is actually also the galactic plane is clearly visible. And then the sky is spotted with objects that could also be stars if you don't know more about it, but actually turns out that all those spots here, or 99% of those, are actually other galaxies. And in those galaxies, as it turns out, it's actually supermassive black holes mostly that produce gamma radiation. How exactly is not yet well established. And overall, you have more than 5,000 such objects that you can, if you dissect this image and you take out the individual components, then you can distinguish over 5,000 objects. And then you, of course, also have this extended emission along the Milky Way that you can explain with charged particles interacting with the gas and dust in the Milky Way, and then producing, again, gamma radiation. And if you take out everything, and this is what has happened with the Fermi data, you remove everything that you know, and then you see what's left. And this you can see in that picture. This is the resolution is a bit worse in order to amplify the structures that you can see there. And you also see that maybe there are a few holes along the galactic plane because there's so much stuff that it was actually difficult to remove it properly. But then you're left with those two lobes below and above the galactic plane. This is a quite extended structure. And you might wonder, what is this coming from? And then if you go to an artist's impression, which I have on this slide here. So again, to remind you, we are actually looking from inside the Milky Way. We can look out to all directions. We can look the short way or the long way through the galactic center. And then if we look up around 45 degrees or down around 45 degrees towards the galactic center, then this is the edge of the lobe in the bottom and on the top. This is at least seen as a strong hint that probably this black hole, such a star, the galactic center, is responsible for emitting very energetic particles that then from up here emit gamma radiation that reaches us on Earth. And if this has happened, then it probably happened a million years ago. What I mean happened is that somehow now the galactic center is very calm, so to say. So you have those infrared flares that Felix has shown you that let it light up slightly in infrared, for example. But it doesn't even get brighter than this star S2, and star S2 is just a star, maybe a brighter one, but it's a star. It also emits X-ray radiation, and it's also variable there, but it's nothing compared to other objects from other galaxies that we know. So what we're really interested in is what happened back then, and could this happen again, and how does this all fit together? And well, we can, of course, observe such objects with the Fermi satellite. And I told you that it's about 1 square meter in diameter. And it's not very well in terms of resolution, angular resolution. Can we do better? And can we also go to higher energies? And this is where magic comes into play. And here I have an example. Sorry that this slide is maybe a bit more technical, but let me guide you through. So imagine you have the strongest gamma ray source, or strongest steady gamma ray source in the sky. This is the Crab Nebula. Here, this is not gamma ray, but an optical image of that object. But it turns out that the strongest source in the sky that's always shining steadily is this one. And if we then look in this graph here, you have energy on the x-axis, and you have particles per area and unit time on the y-axis. And then you just look at these ranges in energy. So from here to here, so this would be 100 to 200 MeV. You would receive something like 4 photons per hour. This is not a problem because the Fermi satellite is scanning the sky all the time over years. So you can accumulate enough data to make a picture like we've seen this all-sky view. But then if you go higher in energy, the red line here is the spectrum of that source. If you go higher in energy, then from a similar, in relative width here, from a similar window, you just have 1 particle per day. So it gets tougher. You have to integrate, so meaning observing for longer time. And then if you go to the TeV range, I've marked here the maximum energy that the LHC can accelerate protons to. That's here, that's even a bit above. But already here, you're down to only 3 particles per year, and there it gets really hard. And this is why you usually say that the Fermi energy range ends about here. at 100 GeVs. Of course, it can go to the TeV range, but then it has to integrate for a very long time or absorb very bright sources. But this is then where the energy range that MAGIC is sensitive to starts. And MAGIC is an imaging air Cherenkov telescope. What this means, I will come to in the next slides. And what it allows you to do is go to higher energies and also achieve somewhat better resolution, by far not as good as an optical or infrared, and also not radio, but still a better resolution. And now we should see a video. Maybe you can play that for me now. Here you see how this technique works. So a gamma ray is entering the Earth's atmosphere from outer space. It basically never interacted until it first hits an air molecule. And then it forms a matter-antimatter pair, electron and positron. And those again emit photons of slightly lower energy than the primary one. And then this multiplies and multiplies. Photons make electron-positron pairs, and they make more photons. And this continues and continues until you've used up all your energy. Always basically roughly split your energy in two in every step. And then all the charged particles, they emit light, so-called Cherenkov light. This is something I will also explain later. Then this Cherenkov light continues, even if the particle shower already stopped higher up in the atmosphere. The Cherenkov light continues until the ground. And if you place there a very big instrument, a very big mirror, you can collect that light. And this is where the video stops. And I will come to my next slide, where I just want to go very quickly over this Cherenkov effect, what this is. This is something like the optical analogon of a jet fighter exceeding the sound barrier. So a plane emits a lot of noise, and these sound waves only travel with the speed of sound. And then if the plane reaches this same speed, all those sound waves overlay and form a shock front that you then hear on the ground as a sonic boom. And a similar thing happens if charged particles travel faster than the speed of light. Such a thing can happen, for example, in a nuclear reactor. And this is then seen as a light phenomenon, typically a bluish glow. This is what you see here. And how can we then use this with our instruments? Here again, you have this whole process displayed in one diagram. So the particle enters from the top, then it forms this vastly extensive air shower with all the particle tracks in here. And every single track there is a charged particle that emits Cherenkov light. And then the Cherenkov light is mostly emitted forward, actually in a very narrow cone of only around 1 degree. So this is exaggerated in this image to keep it compact. Then the light travels to the ground in this wave here, and you can collect it with telescopes. So how this looks time-wise on the ground is shown in the top right here. Every of those animations here and down there only cover a few nanoseconds. So it's really roughly less than 10 nanoseconds in this image. And this is exactly what your camera then sees. If it watches not exactly on axis from below, but with a slight offset, you look into this slightly from the side, typically, and then you see an image in your telescope like this. And if you use many telescopes, not only one, then those ellipses, they lie in different positions, depending on the relative position of your telescope to the direction and impact point of your original gamma ray. And you can use this to better reconstruct the position where this gamma ray came from. And this is also why imaging air Cherenkov telescopes actually can resolve relatively well the direction of origin of a gamma ray and achieve a better resolution than Fermi, for example. And yes, now finally coming to the telescope that is the main protagonist of this talk and that we are using in our collaboration. Those are the two MAGIC telescopes. As I said, for stereoscopy, you use two telescopes. They're spaced by around 80 meters. They have a huge main mirror of a diameter of 17 meters. You've heard that in Paranal, the optical telescopes are 8 meters. You cannot directly compare this because the quality, the optical quality doesn't need to be that good for this technique. And also the resolution of your camera doesn't need to be that good, at least in spatial resolution. They have a parabolic shape, and they are formed of single facets, 247 of those of 1 square meter. They also have a very lightweight structure made from carbon fiber and weigh around 70 tons. This is so they can turn 180 degrees in 20 seconds. This is not so relevant for observing the galactic center, but for other astrophysical events called gamma ray bursts, where you have to react very fast if you still want to see them. They are located on the Canary island La Palma, on a mountain that's around 2,200 meters high. And the most important, technology-wise, most important thing or most remarkable thing about them is their camera. This consists of only around 1,000 pixels. Doesn't sound very impressive, no? But those pixels are photomultipliers, and they allow you to do a frame rate of around 2 billion frames per second. This is another view of the camera. So now we come to observations with such telescopes, but before we come to the MAGIC results, we also have to mention that there are other telescopes around the globe using the similar technique or the same technique. And the first did quite some remarkable research on the galactic center, were the HESS telescopes, and still are the HESS telescopes. They are located on the southern hemisphere in Namibia. And this is an advantage. We'll come back to this later, because the galactic center is actually a southern source. So it can only be seen high in the sky if you're on the southern hemisphere. And from the northern hemisphere, it will only stay close to the horizon, which has implications for the worse in some sense, but also for the better if you want to have something special. What HESS has seen in this region is, this is just the image as it is, as they observed it, accumulating very many of those very high energy photons above roughly 1 TeV in energy. So this is reaching the energy scale of the Large Hadron Collider. And you have a point-like source here, as it seems, very bright. There are also some other sources. And then if you, again, you do the same thing. So you subtract what you already know. You subtract that one and that one as a point-like source. And then what pops out is extended gamma ray emission. Again, this is the galactic plane, but it's a zoom in. It's only a 2-degree window roughly, or a bit more, 3-degree window around the galactic center. And you see that it seems that there is like an echo, or this region is illuminated with gamma rays. And this is also what one thinks that's happening there, is that cosmic rays at some point, maybe around 1,000 years ago, might have been accelerated. This is the hottest candidate, at least, by the black hole at the galactic center. And since then, they're streaming outward and interacting with the gas in this region, and then emitting those gamma rays. But now we come to the second video. Actually, the chain of events that set off or triggered the observations of the galactic center by MAGIC. And this was exciting news in 2012. Scientists working in infrared again from ESO and also MPE, they published data on a gas cloud that could be seen traveling towards the galactic center on a very steep orbit, which would bring it very close. Just showing this, just show it again. Bringing this gas cloud very close to the galactic center, and then leaving the possibility that it would interact with a black hole there. And yeah, no one really knows what, or knew back at the time what would happen in this situation. And then we said, okay, yeah, let's take our chance and let's observe also with MAGIC the galactic center. And what makes MAGIC special in this sense, this is what I already mentioned, is that in contrast to, so now I'm again back to the slides, from Namibia, if you look towards the galactic center at the right time, then it goes nearly through zenith, or very close to zenith. So you just look up. While if you're on the northern hemisphere, where La Palma is placed, you look towards Sagittarius A star, even under the most ideal conditions, you still have a very inclined direction relatively close to the horizon. More precisely, this is a distance of minimum 58 degrees from zenith. And if you then come back to this picture with air showers, if they come from straight up, they are very close, they evolve very close to your telescope, and you get a very dense shower of Cherenkov light onto your telescope. While if you observe them closer to the horizon, then they emit this light much further away, and this light then diffuses out more. It distributes on a larger area, leaving you only with less light to detect with your telescope. But on the other hand, you have to imagine that if this one that comes straight from above, if it's only misplaced by 100 meters, 200 meters, you already miss it. While in this case, if you misplace this one by 100 meters only, it doesn't affect you much because you're still inside this light pool with the telescope. So there's two implications. We have to go for higher energetic air showers. This is not so much a problem for MAGIC because MAGIC has a very large mirror area already and an intrinsic very low energy threshold if you're close to zenith. And you can see air showers from a larger area, meaning that, again, going back to this picture, where I showed how many particles you expect from a square meter. If you have more square meters, you can get much more particles in a short time. And this is interesting if you want to see or search for variability of such an object. So what do we see? Now we're coming to the MAGIC observation campaign that started in 2012 and is still ongoing until now. So this is now the MAGIC picture of the galactic center, as if you combine a larger data set collected over many years. Again, in this plot, this is of course zoomed in, but it has the same coordinate system. So you have galactic latitude, so up and down from the galactic plane on the y-axis, and then left and right on the x-axis. And here I have for you as a reference that the span of this arrow here is 2 degrees. And this is really if you would stretch out your thumb on the arm and just look at the width of it at the stretched out arm. This is roughly what this image here covers on the sky. So it's much more than a football stadium on the moon, definitely. It's even more than the moon. It's 4 times the moon, roughly. And again, also inputted here are the contours of the density of gas in the region that we know from radio observations. Those are the white lines here. And you see that this matches quite well with the intensity of gamma rays observed with MAGIC, especially after you would remove the 3 objects or sources that we assume as point-like here with the colored markers. If you remove those or would remove those, then you would only be left with a structure that follows these contours roughly. Okay, but now what about this G2 cloud? From observations and simulations, it was predicted that the closest approach to the black hole would happen in 2014. And of course, MAGIC was observing through that period. We cannot observe during all seasons, but only in spring and summer season, simply because otherwise the sun is up while the galactic center is up too. And this technique, I didn't mention it before, but it only works during the night. We probed this at 2 different energy levels. One was around 1 TeV, and the other one was above 10 TeV, so lower energies and higher energies. And we checked if there is any variability. And but as you can already see, around this closest approach to the pericenter, there was not really, at least not in a significant way, a change of the brightness of this central object. But we could also use this data set to perform other studies. So this would have been an immediate reaction here if we would have seen the black hole brightening up in gamma rays. But I've already talked about this gamma ray echo in the surroundings. And there have also been in the meanwhile new observations from Hess and also these observations by MAGIC now. And you can now study this a bit more in a quantitative way. You can look at here, this is a graph that shows you the required intensity of cosmic rays that is needed to explain the gamma rays from a certain region. And the region by region is meant the distance from the black hole. So the further you go out from the black hole, the less brightness or the less intensity of cosmic rays you need to explain the gamma ray brightness. And this follows this mathematical function here roughly. at least. So within Eros, you can say that it follows this profile, and it's brighter, close, so more cosmic rays close to the black hole and less further away, which is further supporting this theory that about 1,000 years ago, depending on the exact model you use to describe this process, somewhere at the galactic center, most probably close to the black hole, cosmic rays have been emitted in vast quantities, and then since then are diffusing outwards and are now basically creating kind of an echo from the surrounding gas clouds in gamma rays, because they interact with the molecules and produce gamma rays. And last but not least, we can also ask about the energies of those protons, first of the gamma rays, and then also of the protons behind that, by sorting basically the events we observe. We sort them by energy, and we see how much we get for which energy. Here you have again, this is basically the amount of energy that is emitted into a certain band of energy. So basically, if this is flat, like here for the first few data points, it means that the amount of energy that goes into gamma rays in this energy range and in this energy range and this energy range is about the same, and then it slightly drops off towards higher energies. And what energies are we talking about? So again, here, roughly at the center of this plot, this is the highest energy that could be reached by protons accelerated at the Large Hadron Collider, 7 TeV. But then again, if you would use those protons and you would shoot them at the molecular gas around the galactic center, then the gamma rays produced by those protons would be of lower energy, only roughly here. This energy is what you would expect from those protons from LHC. So meaning that if protons, which is nearly out of question now, are responsible for the gamma radiation at higher energies, they must have much higher energies than the ones accelerated at the LHC. And how high? Well, there was a paper published by the Hess collaboration in 2016 suggesting that it could reach as high as 1,000 TeV. This is about 150 times the energies reached at the LHC. Then further observations by the Hess telescopes and also now our observation data set show that if you look at a slightly larger region also, to be fair, this is also why the level here in terms of intensity is a bit higher, you actually start seeing something that looks like something we call a cutoff, so a maximum energy that you cannot exceed, that maybe the accelerator at the center is not able to exceed. But it's still, with those data sets, it's not 100% clear if there's really a limit or if it continues maybe just with a bit steeper slope. Yes, so this is our state of knowledge about this very unique gamma ray source, because we have only one center of our galaxy with only one black hole that is so close. Yeah, so that's it for now from Magic. And stay tuned. And here, just as a teaser, you see this montage here with the Magic telescopes down here, and already all that CTA, which is the successor instrument or a new instrument that's being built also in La Palma. One telescope, actually that one is already there in real life. The others are being constructed and will hopefully even improve our sensitivity to those objects. Yes, that's it.
Okay, thank you so much, Christian, for your presentation. The time is flying. We have already been talking about the black hole for 1 hour. I haven't been bored, so I hope the others haven't either. And I think we got some questions during both of your presentations. Yes, so we have one question by Elisa. I think it's directed to Felix probably, and she's wondering how the data taking shift looks like in Chile.
Yeah, so we actually still go, if there's no COVID, we still go to Chile and are at the observatory in person. So we usually a couple people, and you stay there for something like 10 days usually. And then depending on the time of the year, you have like 5-6 hours of observing per night. And but Paranal is a great place to be. It's like a little village full of astronomers in the middle of the desert of Chile with amazing night sky. I really like being there, and I'm looking forward to go again as soon as possible.
Thank you. And I think it would be worth to also talk about the observation shifts at La Palma, because we probably also have people here who don't know about magic and the observation shifts. So maybe, Christian, you've been on a couple of shifts in your life, I think. So maybe you could also talk about that.
Yes, I've been there. Actually, it's already a while ago since I was really on shift, maybe 2-3 years already. But some things have changed due to Corona, probably. But still, it's a very nice experience. It's quite exhausting. You work throughout the whole night. Typically, we have 4 or 5 people on La Palma, so that also people can take off. You have to have at least 2 people working at the telescopes in the evening, and for shutting down the telescopes in the morning, you need 3 people on site. If everything goes well, it can be quite boring. Usually you're very happy if things are boring, because if they get exciting, usually means that something is going wrong and you have to interact with the hardware. It can also be that you have bad weather and then you cannot not operate the telescopes, or you're waiting for the weather to improve. And very often you wait, watch movies, but you socialize. It's actually quite a nice experience.
Yes, I can actually comment because I spent quite some time on La Palma this summer. Even in spite of COVID, it's still a lot of fun. I can promise you that. Yes, it's a great experience for all of us members of the Magic Collaboration to get to see the telescopes, and I guess it's the same for gravity. I mean, it's just amazing to have the possibility to really see the instruments and operate them yourself, right?
Yeah, it's especially with the 4 UTs in Paranal, it's amazing to be there and observe.
Yes, it's one of the peaks of our job, I think. Okay, so we had another question by David. He was wondering, I think this was directed at Christian, if we are able to detect Compton effects from relativistic particles.
Yes, so you, of course, see Compton effects from relativistic particles. The problem is usually to tell this apart from other processes. It's usually a priori, it's very difficult to tell if this, what you're looking at, you see gamma rays, but you don't know if they come from hadronic processes, meaning mostly protons interacting with molecules or atoms, or if it's actually electrons. Those electrons can do several types of interactions. For example, they can also do Compton effect, or photons can be emitted through inverse Compton effect. The only way how we can really see, thank you, showing this. The only way, this is now the inverse Compton effect. So basically an electron transferring energy to a photon and then leaving the photon with higher energy. There's one way how we can distinguish. This is actually outside of the magic energy range, but more in the Fermi energy ranges, where we can see that it stops at a certain energy and not at high energies, but at low energies, meaning that the energy for producing pi zeros, this is a decay product or a product of the interaction of protons, is not able to be formed, or it's you have to at least invest a certain amount of energy in order to produce a pion, and then you get this energy back in terms of photons if this pion decays, and this would create a cutoff at the lower side of the energy spectrum. But apart from that, it's very difficult from those alone. There's one messenger, because I'm working in neutrino astronomy, I have to say this, that of course, if you have protons interacting with protons, you would also produce, or you are also producing neutrinos. For those, you need different instruments, of course. Those neutrinos you don't get if you have electrons only.
Okay, thank you. Thank you, Christian, for answering this. Actually, I think we have a follow-up question by David on the shift in Paranal, because he says, well, if it's only 10 days and the trip alone is probably 2 days, why are your shifts so short, given the distance that you need to travel?
That's actually due to ESO. So ESO, the European Southern Observatory, who runs the telescopes, that's due to their regulations. So first of all, you're not allowed to be on Paranal for longer than 14 nights, I think, because it's so excluded and so high, you have to leave Paranal every 14 nights. And the second one is that only about once a month there is the possibility to observe with the VLTI. So using gravity, using the 4 telescopes together is the Very Large Telescope Interferometer mode. And this has to be specially scheduled by ESO. So normally during the normal time, you can only observe with single telescopes. And then they have this 10-day blocks where they allow VLTI observations. And that's usually when we are on the mountain for the gravity runs.
Okay, yeah. Okay, so there was another question by David. How close to the speed of light must these particles be traveling? Is that related to the cosmic rays that produce the gamma rays? Or I'm not sure which particles he means exactly.
So those protons, so if we talk about the particles that are accelerated and then interact with gas and produce gamma rays, so the cosmic rays themselves, this is something I cannot even tell you. This is so close to the speed of light. This must be something 99.999 and add a few more if you like, percent of the speed of light. For particles in the atmosphere to emit Cherenkov light, is of course again, it doesn't. Of course, it does depend only on the refractive index of the atmosphere. And they're higher up, they need to be a bit faster. Further down, they can be slower. But this is on the order of again 99.9% of the speed of light. But I don't know it by heart. In water, for example, they could be, so you've seen this picture of the nuclear reactor, there you can live with only 70% of the speed of light. That's already enough.
Okay. I think maybe worth to mention here, so if we talk about Cherenkov light, actually the particles are traveling faster than the speed of light in the respective medium, right? So,
True.
I mean, the numbers you were saying, like really close to speed of light, were always, in respect to speed of light in vacuum. But actually, if you enter into a medium like water or also the atmosphere, the speed of light is reduced. So that actually enables charged particles, right, to be faster than the speed of light, and that's when the Cherenkov effects happen. So this is always it's a nice, actually really nice physical phenomenon, I think, and always mind-blowing to people who don't know the details, like, what, faster than the speed of light? Well, yes, it's possible, but only in a medium, not in the vacuum, yes. Okay. I maybe wanted to quite quickly discuss with you, because you've mentioned that the views that you two have on the galactic centers are very different, and that the resolution of magic is very different, and well, worse compared to gravity. I was just wondering, maybe we can together put this into context for people who are not familiar with the units that we use. So when Christian was talking about degrees, so you were showing us 2 degrees, how many milli arc seconds is in 2 degrees? I mean, just to give the people that are watching an idea of the difference we're talking about here.
So what I was using as the smallest unit was micro arc seconds. And you can basically split up a degree similar how you split up an hour. So from degree, 1 degree is equal to 60 arc minutes. And 1 arc minute is then again 60 arc seconds. So 3,600 arc seconds are 1 degree. And then you have to add a 1 to the power of -6 to end up at the micro arc seconds, which I was using. So that's the special thing about gravity, is this insane resolution which you get.
Yeah.
So you're a billion times better, basically.
Yeah, I think that's it's good to get that image in your head, that it's a really big difference, but still both looking at the same object, and really still the physics that you do is still talking about the central black hole, right? And I think that's just important to put into relation.
Yeah, it's also if people talk about the galactic center, they speak about very different things usually, because if I mean the galactic center, I really mean the tiniest region around the black hole. And then if you say galactic center, you're going out to a degree, which is pretty
For
big
you,
for me.
it's just crazy, something completely different. Yes, that's a good comparison. So we have €1 on the moon versus 4 moons. That's more or less the difference we're talking about. Thank you, David, for this for this quick calculation. Okay, so I think we don't have any more questions from the audience. So I will have one final question for you two. What is for you personally the most fascinating thing about the Galactic Center? Why did you choose to study the Galactic Center? Who wants to start? Let's start with Felix.
So for me, the really interesting thing is the time scales and what's going on, because usually if you do astronomy, then you look at galaxies which evolve over billions of years and you just see a very tiny snapshot. But with the Galactic Center, you have these stars flying on 15-year orbits, or for example, the video which I showed of the flare, when you sit at Paranal during a night and you see the black hole in 30,000 light years distance flaring up through some insanely energetic event. So that's really from a science point of view, what makes me super interesting about the Galactic Center is that you can, within a night, observe changes, and there is so dramatic physics going on, which we haven't really understood. So that's a really cool thing to work on.
Yes, that sounds pretty amazing. Okay, so Christian.
Yeah, so for me, it's just the fact that, well, there's not only one supermassive black hole out there. We know that most of the galaxies have one at their center, and we also know that a lot of those are much more active than our galactic center. But our galactic center is just much closer to us. So it's if we have the chance to resolve, and this of course mostly happens in other wavelengths where the resolution is much better. But if we want to resolve something, then we have a much better chance if we look at that one. Then, of course, it is also that if we look at extragalactic supermassive black holes, we can only see the ones in gamma rays that are super active. And the one at our galactic center is basically the only one that's in a calm state that we still can study in gamma rays. And then last but not least, it's also this cosmic ray riddle, basically, that we observe cosmic rays, something that was never mentioned in this talk, but these charged cosmic rays, they also reach Earth. We know that they're there, but because they are charged and deflected by magnetic fields, they could come from anywhere. And we don't really know from where. We have a few candidates, but it cannot really make up for everything. So there we have one candidate that could at least explain a quite large fraction of it, potentially.
Yes, so a way to try and solve one of the biggest riddles, I think, for us astroparticle physicists, like this origin of the high energetic cosmic rays. It's one of the questions that drive us in our research. Yes, okay. Thank you too. I definitely had a lot of fun. I hope the people who watched also did. I learned a lot. Thank you, Felix, for your amazing talk. And also Christian,
Thank you for having me.
Yes, thanks for agreeing to join us, to both of you. And maybe also a quick thanks to the people, the two ladies that were pulling the strings backstage. So maybe you can quickly show your face. Hi. Thank you too for making this a smooth event. And yes, I think with this, we stop. Thank you, everybody, for joining. Thank you for the discussions in the chat. And thanks again for our two speakers. Goodbye.
Bye-bye.